move on to our third part, toward heterogeneity aware machine learning. And actually, this is the main part of our tutorial because actually part 1 and part 2 are both about some preliminary literatures or. And here we have some recap of the terminology. And here the shift refers to the mismatch between training distribution P and the target 1Q. And also, distributional robustness refers to model performance not becoming worse even when Q is different from P. And also, heterogeneity refers to the diverse mixture of distributions that generates data, including both training and the target. And until now, we have introduced many things, but what's left? And actually, how to measure the data heterogeneity and also how to analyze the shift patterns. And these two things we haven't introduced the tools in detail. And in this part, we'll introduce many algorithms and tools. And for systematic view of machine learning pipeline, and we specify 4 stages. And for the stage 1, we would like to analyze data heterogeneity before we're making modeling assumptions. That is, after we have collected many data, and we would have to analyze the property of our data before we build our model and before the model training. And here's our first perspective. It's important to understand if your data has heterogeneous subpopulations. That is, after collecting data, we really need to know whether our training data contains subpopulations with different y-given-x. Because if there are different prediction mechanisms, then we may have to use different models to model them. Yeah. And in contrast, invariant learning methods, they assume the same x to y difference. They assume the same x to y prediction mechanism across the whole population. And this assumption may be not suitable for many practical scenarios. And let's move on to our first tool is the predictive heterogeneity. And actually, it's a very first try in this direction. And we hope this example of work could inspire some further research. And the high-level idea is that it tries to divide the whole data set into different subgroups with different y-given-x distributions by maximizing the additional useful information gap. And here's the definition of our term. And we can see that it divides the data set into different parts. And here the E is a kind of split. And the first term is the conditional mutual information. And here we calculate the gap between the conditional mutual information and the original mutual information. And we try to maximize this gap and to learn such of split. And we hope that by dividing the whole data set into different parts, we can explore even more predictive information. And here we give some preliminary about mutual information. And actually, the mutual information, it captures how much uncertainty could be reduced after we have the information of covariance X to predict Y. And here, HY denotes the entropy of Y. It measures the uncertainty of the variable Y. And also, the HY given X denotes the conditional entropy of Y given X. And it measures how much the uncertainty left after we have access to some feature sets. And therefore, the mutual information compares the gap between these two terms. It captures how much information X can provide to reduce the uncertainty of Y. And also, for the entropy of Y, it also can be viewed as the hardness of the original prediction task. Because the more random of Y, it means that the task is more hard. And then, actually, from our definition of the predictive heterogeneity, we can see that the second term does not rely on the E. And then, during the optimization, we do not have to care about this term, and it's only about how to maximize the conditional mutual information by learning some kind of split. And here we expand this equation, and it's like this. And we can see the left line, and we split the whole data set into different environments or subgroups, and we calculate the mutual information in each of this group, and then we sum them together, and that's the definition of conditional mutual information. As for the algorithm, from our objective function, and we can derive our algorithm, and it's bi-level foundation algorithm to help to learn such kind of environment split. It's kind of just 2 maths on it, and we just skip it and to the experimental results. And here we first use an example from the application of agriculture, where we want to predict the crop yields from some climate features, like the temperature or some wind speed or something else. And in this task, it's clear that actually the crop type it affects this prediction task. But for our prediction model, we do not have this feature, and it does not know about the crop type. And in the last figure, we draw the true division of 2 crop types around the world. And on the for the right figure, we show the 2 subpopulations learned by our predictive heterogeneity. And we could see that these 2 figures overlap a bit. And the predictive heterogeneity actually learns subpopulations with different crop types. And further, in this situation, we should not pursue the invariance anymore, because actually for different crop type, maybe the prediction mechanisms are quite different. And it's a better way to like divide and conquer. And the second example is about healthcare or COVID-19. The task is to predict the mortality from some symptoms and some underlying diseases of patients. And first, if we do ERM over all data, and the top 4 features are like SpO2, which refers to the degree of blood oxygen of the patient, and also the renal diseases, neurologic diseases, and some diabetes. And this makes sense since many people died because of some underlying diseases. However, when we use our predictive heterogeneity to split the data into like 3 subpopulations, and in the last figure, we draw the age distribution of each of these groups. For example, for the red curve, we can see that there are mainly people like over 70 years old. And for the top features of this group, there are mainly some underlying diseases. And this makes sense. And because according to our knowledge, people died, some elder people died because of their underlying diseases. However, for this pink curve, we surprisingly find that it spans over all age groups, like from younger people to some older people. And if we examine the top features of this group, like in this red box, and we find that they are not about underlying diseases. There are some serious COVID symptoms, like fever, cough, renal, or something else. And this aligns with our knowledge. That is, if COVID-19 itself is really severe, it will cause death to people from all ages, not only the older people. But if we do not analyze data heterogeneity here, and we just learn one model by empirical risk estimation, and we cannot realize this kind of causes, and it may cause death to some younger people. And here for summarize, also this work has some limitations, and we need more efficient ways to discover heterogeneous subpopulations, and we need to scale up to some larger tasks and models. And also the next goal is we need to understand heterogeneity even in more detail, because for example, why do they have the Y-given shifts that's in our empirical study? They may be because of some unobserved confounders or some different generating process. And also, how do we derive corresponding solutions to each kind of these reasons? And there are all some reflections that and also then we move on to the second stage is the model training stage. And our goal is to analyze data heterogeneity and incorporate data heterogeneity into model training. And here we provide two examples corresponding to the two branches of methods we discussed before. The first one is for invariant learning. Recall that RM does not outperform ERM on many image datasets. And here we would like to analyze the reason behind this. And we think the reason may be because of the quality of training environments. Recall that the invariant set is defined as this, where each predictor in this set satisfies some invariance property, and this property is relies on the invariance E. But what happens when this invariance E is replaced by some training environments like E-train? Because for training environments, it cannot cover all of the possible environments, and therefore the resultant invariant set will be much larger than the ground truth invariant set. Then, if we find the maximal invariant predictor from that set, it means that actually it's not invariant. It may contain some like sparse features or something else because the quality of our training environments is not good. For example, if all of the environments in our training set are exactly the same, then we cannot obtain any kind of invariance. And also, even a more severe problem is that for most of the cases, there's no training environments because modern data sets are frequently assembled by merging data from different sources without explicit source labels. And which means that there are not multiple environments, but only one pooled data set. Also, actually, we do not know how to define a good environment because maybe it's not the ideal way to give the source label as the environment label. Therefore, the second perspective of our tutorial is to explore heterogeneous environments during training. And here we just show one very first work in our group, which is called heterogeneous risk minimization. And the overall architecture is like this, and it involves two modules. The first one, MC, is a clustering module to split dataset into different parts. And the second module is MP, denotes the invariant prediction model. It tries to do the invariant prediction based on some learned environments E-learned. And these two modules can boost each other, and we may learn better environments, and also we can learn better invariant predictors. And for this part, actually the heterogeneous environments can be viewed as a special kind of data heterogeneity here. And for the heterogeneity identification module at the MC, the goal is to use some unstable features as input and generate some learned environments. And here we use some kind of Gaussian mixture model to capture the different relationship between the CX and Y. And therefore, the learned environments will capture different prediction mechanisms. And after we have this kind of E-learn, we can input to our prediction model MP to produce some invariant predictors. And also, in this loop, we can only do some on the raw feature level because actually we do some feature selection. And for the prediction model, we just try to select invariant features. And if we have selected the invariant features, and then we know the variant features because it's about feature selection. And then the variant features will input to the clustering model to produce the heterogeneous environment. And here are some results, and I'd like to show some results on the color remedies, which is super interesting. And look at this figure, and the blue curve denotes the amount of heterogeneity between two learned groups from our method. And we use KL divergence here to measure it. And the red bars denotes the target accuracy. We can see that along with the interaction between two modules, they can boost each other. And more interestingly, the target accuracy is consistent with the heterogeneity. Like the red bar is consistent with the blue curve. And this further demonstrates that a better understanding of heterogeneity or the exploration of heterogeneity could help model training and generalization. And this work has inspired many following works on various tasks, like in recommendations and also for the graph data. And if you are interested in any of these topics, you may take a picture of this and refer to them after our tutorial. And then we come to the second example for DRO method. Recall that DRO does not outperform ERM on tabular data, and they cannot either outperform tree-based methods. And recall that there's over pessimistic problem of DRO, and here we provide another example. It's about a binary classification task. Here, as the radius of the ball become larger, and we find the confidence of the DRO model approaches like 50%. Actually, for a binary classification task, the confidence is about 0.5. It means that the model refuses to make any predictions. So why this happens, and we think one key reason behind this is the noisy samples. And here comes our third perspective, is to avoid noisy samples during model training or in DRO. And here we showcase two typical DRO methods via a toy example, where we have a majority group and a minority group and some noisy samples. And we find that both DRO methods, they align too much sample weights to noisy samples. This is not desired, since our model cannot learn anything from noise. Therefore, to enhance the empirical values of DRO methods, we really need to avoid noisy samples. And this can be viewed as another kind of data heterogeneity here. It's about hard samples and noisy samples, because they both have high prediction errors. And then we use a simple weighted least square model to prove that if noisy samples gain too much sample weight, the parameter estimation will be quite random. That means that our model cannot learn anything from noise. And so how do we avoid noisy sample problem in DRO? Recall that DRO will focus on samples with high prediction error, but both hard samples and noisy samples have higher prediction errors. So how do we differentiate them? The main idea is that we need to leverage data geometry information. And to do this, actually, our main assumption is that first high-dimensional data lie on low-dimensional manifolds, and also noisy samples are mainly some isolated points. It occurs randomly in our data set. But hard samples or minority group samples, they are continuous within a neighborhood. For example, the neighbor of a hard sample may also be a hard sample. And then we propose a new kind of metric named geometrical Watson's distance to capture the geometry properties of the data distribution. And different from the original Watson's distance, in this distance metric, first the support of samples are restricted to a graph node, and also the math can only be deployed along with the manifold, rather than using some Euclidean distance. And also from this constraint, we can see that the densities can only transfer uniquely along the manifold. And here we give a simple figure to demonstrate the difference between geometrical Watson's distance and F-divergence and also Watson's distance. For example, for the yellow curve, it's about the F-divergence, which does not care about the data geometry. It's like it only cares about the density, and we just open a tunnel to transport density from one sample to another. However, for Watson's distance, it's like this red curve, and it only cares about the Euclidean distance from 2 points. However, for geometrical Watson's distance, the transportation can only be done along the graph or along the data manifold. And this is the key difference between these three kind of metrics. And also, we need to add some calibration terms to explicitly avoid noisy sample. And here we add a term is the graph total variation. And this term penalizes noisy samples. And together with these two terms and a new distance metric, and here's the results of our method. We can see that compared with the previously two DRO methods, in our method, the sample weight on the noisy samples is much lower than before, and therefore our DRO method will pay more attention to the minority group, and it may achieve better performance. And also here's a side product. It's about the free energy implications. Recall that the first equation is our objective function. It has three terms, and we find that actually these three terms exactly corresponds with the three terms in the free energy function. And in this way, we can unify the DRO methods via free energy function, and also it provides a unique understanding of different DROs with different distance metrics from a free energy perspective. For example, different DROs may have different kinds of energies and different forms of each kind of energy. And then we come to the fourth perspective of our tutorial. It's about DRO tailored for specific shifts. And it's another kind of data heterogeneity. Here is about we should understand the shift patterns first, and then to come up with the set of DRO or the set in DRO. And for example, here, this example has appeared in part 2. And in this example, we consider the shifts induced by age groups, like people from different ages. And for DRO methods, we first do some variable selection according to our validation set to pick up the variables that whose distribution shifts the most between training and target. And then we only perturb features, and then we only perturb these features. And we find that actually for some of the selected features, we can see for example, for Watson's DRO, it performs even much better than some previous methods or some previous methods. Compared with the original version of Watson's DRO, it's this dark green bar. If we compare with the light green bar with dark green bar, we can find there's a huge improvement. And also for YT-max shifts, we also find the same improvements. Let's consider a public coverage data set where the task is to predict whether a person has bought like a health insurance. And according to some other paper, we find that one first feature is the income feature, because the income level between different states are quite different. And if we use income feature to predict whether a person will buy health insurance, and it cannot be transferred to other states because of the different levels of income. And therefore, for the building of DRO methods, we can only perturb the relationship between the outcome and this income feature. And actually, we find that compared with DRO that builds on all of the features, if we only care about the outcome and the income feature as the last bar, there's a huge improvement over the previous ones. And the performance is comparable with some previous methods. And this perspective shows that if we have a better understanding of our shift patterns, and if we can analyze our data heterogeneity first, then we may have a better modeling way to design different kinds of methods, and they may work more efficiently in practice. And then we come to the third stage about model evaluation. And we give two examples. The first one is the error slice discovery. And our perspective is that it's important to understand where a model performs poorly. Because for typical evaluation protocol, people just calculate some accuracy or F1 scores over all the test data. But there's not much information inside a single score. And actually, after training a model, we really need to know what kind of training data does the model perform poorly. And if we understand this, we can do some efficient data recollection and also some model patching or retraining. And also we can inform the users, please do not use our model on certain regions of data because you cannot trust our model on that kind of data. And actually, the slice discovery method is a line of research and is defined as an algorithm that finds slicing functions which split a dataset into some underperforming slices. And there are many literature on this line of research, and we will not introduce too much here. And you can just remember that the key idea is to learn some kind of slicing functions to split the whole dataset into some underperforming groups. And for the second example is about stability evaluation. And our perspective is beyond accuracy. We need to evaluate the stability of a machine learning model, no matter what kind of applications you are in. And the key question here is that what kind of data distribution is the model most sensitive to? And actually recall that there are two ways of generating distribution shifts. The first one is data corruption. It means that maybe the distribution support can be changed, although our samples may be polluted or modified by someone else. And the second source is subpopulation shift. It means that there may be some perturbations on the probability density or mass function while keeping the same spot. And then we'd like to first introduce some preliminary definitions. That is called the OT discrepancy with moment constraints. And for the original OT distance, we only compute in the sample space, denoted as the script E. And for this generalized one, we uplift the sample space to a one-dimensional higher space, which is a joint space of sample and sample with of sample Z and sample with W. And then we choose a cost function like this at the bottom of here, and which combines the difference between samples and also the difference between the probability weights. And here theta 1 and theta 2 controls the relative strength of these two kinds of shifts. And then here's our the notion of our stability measure, and it's quite easy to understand. We try to minimize the perturbation distance such that the performance of our model will drop to a predefined threshold. Here R is the predefined risk threshold, and this MC denotes the previously mentioned OT distance. And here we draw an intuitive figure to demonstrate what's it. Actually, it's some kind of projection distance to the distribution set where the model performance falls below a specific threshold. We can see that here for this point, this is the original training distribution, and here we draw a set, and each distribution in this set will destroy our model to a specific threshold. And we just calculate such kind of projection distance, and this captures the most sensitive direction that will destroy our model. And we define this distance as our stability measure. You can see that the larger of this distance means that your model is more stable, because I need to make much more perturbations to destroy your model. And otherwise, your model is not robust, because I just perturb the data a little bit and then your model fails. And after some dual reformulations, we can have a tractable optimization way to calculate our stability notion. And actually, our framework will produce two things. The first one is stability measure that can compare the stability of different models. And the second one is that we could actually find this most sensitive distribution Q star here. And if we have much information about this kind of sensitive distribution. It can inform us why our model fails, and also it can provide some valuable information about how to improve our model, our model. And here we realize on a toy examples about what the most sensitive distribution looks like. And here we consider a binary classification task on the leftmost figure, and we also draw the decision boundary. As for the third figure, we set theta2 to be infinite, and we only care about data corruptions. And we can see that for the most sensitive distribution, it just moves samples close to the boundary. And also for the last figure, where we set theta1 to be infinite, and we only care about subrelationships. And we can see that in this kind of distribution, the samples near the boundary gains much higher sample weights. And actually, our stability measure enables different choices of theta1 and theta2, which could provide a more comprehensive evaluation of stability under different patterns or different mixtures of shifts. And after we, and here we'll introduce some results on how to evaluate, how to compare different models. And here the task is also the income prediction task. We would like to predict individuals' income based on their personal features. And here we examine three kinds of methods. The first one is empirical risk minimization of Valina method. And the second one is adversarial training. This kind of method is designed for data corruptions. And the third one is tilted ERM, and it's designed for subrelationships. And here's the results of our evaluation metric. And we find that actually, if we look at the left side, our measure mainly focuses on data corruptions. And in this case, adversarial training performs the best because it is designed for such kind of shift. However, if we look at the right side, where we mainly care about subrelationships, we find that actually adversarial training performs similarly than the Valina ERM method. It means that a method designed for one class of data perturbation may not be robust against another. And also the same for tilted ERM. It performs much better when we consider about subrelationships. But when we consider adversarial robustness or data corruptions, it performs not so good. And also our framework enables to access feature stability. And we can only perturb each feature each time, and then we can calculate the stability measure to compare the stability between different features. And here we get some results. Again, on the income prediction task, we measure the feature stability of a neural network model and also a logistic regression. And we sporadically find that actually both of the models are sensitive to a risk feature about American Indian. And it's a not desired thing because it may cause some fairness problems. And here the model, they saw someone is American Indian, and they will think maybe he's likely to be a poor people or something else. Yeah. And also, in another example of the COVID-19 prediction, we find that both models are sensitive to some age features. And this reminds us to think that whether these models perform well over all age groups. Because if a model is sensitive to an age feature, it means that if we slightly modify the age, maybe our model will perform super differently. And again, our answer is no, because here on the first figure we draw the accuracy, and on the below we draw the macro F1 score, and we find that even if the accuracy of the younger group and also the elder group is super high, but if we look at the macro F1 score, they are around 0.5. It means that for younger people, the model simply predicts he will not die. But for elder people, the model simply predicts QLI. And therefore, even if the accuracy is high, their macro F1 score is super low, and it's kind of random guess. And also based on the results of our stability evaluation, we can design some targeted algorithm intervention. And first, for some insight, it's like if our model is only sensitive to one racial feature like American Indian, then for adversarial training, we do not need to perturb other features. We only need to focus on this kind of feature. And we do the experiments, and we find that if we do some targeted adversarial training, it significantly improves the worst racial group accuracy. And it's a rather simple way, but it works the best. And now we move on to the last stage. It's about analyze data heterogeneity after deployment. And in this setting, it's like we have already deployed our method in practice, and we have a little amount of target data, but we find that the performance of the model drops a lot. And we need to understand why our model drops and what kind of shifts it is sensitive to. And here we give two examples. The first one is to decompose or to attribute the performance drop into Y-given X shifts and X shifts. And it's our perspective is that it's important to understand why your model performs poorly across a distribution shift. And because there are different kind of methods designed for different kind of shifts. For example, there are domain adaptation methods, DRO methods, inventory methods, and also some data-centric ways like we can collect more data and features from the target. But actually, all of these methods make some modeling assumptions. That is, we have to first understanding our situation, and we have to understand our data before we applying these methods to improve our model. And the key idea is to understand distribution shift to determine our next step. And to understand why model performance becomes worse for model predicting Y-fairness, we want to attribute the change in model performance to two kinds of shifts. The first one is X shifts, and the second one is Y-given X shifts. And X shifts can arise from changes in sampling process, maybe the shifts in population demographics, and it can also arise when your target distribution is a minority group from your training distribution. And for Y-given X shifts, it may arise from like in the labeling process or different prediction mechanism or some poorly chosen X. Maybe there are some unobserved confounders, or there are even some missing features. And actually, real distribution shifts involve a combination of both shifts. And we really need to attribute these changes into each kind of these shifts, because not all the shifts matter, and we need to find some specific way to improve our model. And to do this attribution, the key challenge is how to measure the Y-given X shifts. For example, here we on the first figure we draw the density curve of Px and Qx, and we can see that on some of the X regions we do not even have labels from P and Q at the same time, and it means that the Py given X or Qy given X on these regions are not well defined. Therefore, the key point is that we can only compare Y given X on the shared X, like in this region, because we observe the labels from P and Q at the same time. And to achieve this, we construct a shared distribution on X. And for example, for the age example, it corresponds to people who are not very young and they are not very old. And we can define this shared distribution in terms of density to have the nice properties that it only has support when both training and target have support. And also it has high density where both distributions have high density. And we will not go into much detail here. For more information, you may refer to this paper to discuss some other choices of the selection of this shared distribution. And now let's put everything together and we can get this grid. It has 6 quantities going from left to right. we shift the marginal fx from training to shared to the target. And from up to down, we shift the conditional y(x) from training to target. And we can decompose changes in loss by taking the difference between terms along this body line. Note that we do not take any other path in this grid because the other terms may not be well defined. And in this way, we can decompose the total shift into these three parts. And it's like this. And here we show some kind of results. For example, if we train a model on West Virginia and we test it on Maryland, and it drops a lot, and using this kind of attribution tool, we can attribute the drop into different sources. And during the training, we do not involve the education feature, and which may affect the prediction mechanism. And also, you can see that our this attribution method could attribute the y(x) shift. This method could attribute the drop to the y(x) shift. And also, there are some other diagnosis tools appeared in other papers, and if you are interested in, maybe you can take a look at it. And then we come to the last example. It's about covariance region analysis. And the key idea is that even if we know there are huge y(x) shifts, we need to understand where we have y(x) shifts because it could tell us how to improve our model. And the main question is, where does the model performance drop because of y(x) shifts? And we propose a simple tool to identify the covariance regions with large y(x) shifts. The key idea is we need to find some covariance region, and the algorithm is like this. First, as the method before, we construct the shared distribution on Sx, and then we model y separately on each of training and target functions like fp and fq, and then we calculate the difference in y between training and target on this shared distribution. And then we could fit a simple decision tree to predict this gap. And the result is like this. This is the example I've shared in our part 2. And in this way, we can find a risk region. And on this region, there is huge y(x) shift. And if we look in index of this region, we find that it mainly contains like females over 30 years old, and they work hard every week, and also they are highly educated, and also their works are really some good jobs like financial people, businessmen. However, why this region have the largest y(x) shifts? And we find that maybe it's because the official language are different, and I've shared before. And also, actually, the first time we saw this region, we just input it to ChatGPT and we asked it why this happens, and it tells us maybe it's because of the official language. And then for the first way, we just include the language feature into training, and you can see that actually the y(x) shift disappears. And also, if we have more information about the covariance region, we can collect better target data. For example, we do not have to collect data from the whole target distribution. We only need to collect data from this identified covariance region. And this leads to a more efficient data collection way, and also the performance will be much better than some random collection or some uniform collection from the target domain. And here's some takeaway or recap. That is, data heterogeneity is really important, and there are several existing approaches for better generalization. The first one is to make some modeling assumptions like DRO and event learning, but do the assumptions really hold in practice? We really need to check it. And also the second line is to scale up data. They are effective for internet scale data, but for many important areas, the data are costly and we cannot have so much data. And in the third part, we introduce our heterogeneity aware machine learning, which develop tools to understand data heterogeneity, and also which shows how to integrate this understanding into the whole machine learning pipeline. As for some future directions, first, we need a system level view of AI, and we also need to design better workflows, because in our tutorial, we only specify 4 stages. There may be even more stages, and also we need to combine the understanding of data into each of these stages. And also, we must build models that know what they do not know. It may involve like we need to try to recognizing some unforeseen heterogeneity at test time, like test time adaptation or fast adaptation. I saw another keynote maybe tomorrow or Wednesday is about fast adaptation. And also this connects to uncertainty quantification, like Bayesian machine learning or conformal prediction. And also these are some future directions that needs to be explored. And then maybe we need some better ways to track our data, because for most of the standard settings of machine learning, we just have a fixed data set. But actually, in practice, we need to actively collect data from the environment or from different sources. And actually, we need to decide how to actively collect data to reduce this kind of uncertainty, and also to enhance the generalization generalization ability of our model. This may connect to like reinforcement learning or active learning, and is also the topic of this lifelong learning concepts. And to sum up, we need a system view of AI, and we also must build models that know what they do not know. And also based on this uncertainty, agents must decide how to actively collect data to reduce the uncertainty. And overall, there are all some exciting research directions with many open problems. And I think we hope our tutorial could inspire this line of research. And that's all. Thanks for listening. And I'm really excited to be here. Yeah, and that's all. And if you have any questions, you can just ask me, maybe. Yeah. Yeah, please.
Thank you for your presentation. I was wondering how much of your work depends on actually having features that describe it differently. Because, for example, when you talk about noise and the undistributed, maybe some undistributed data looks like noise because you don't have the right features there. But I wonder whether you could comment on that.
In our work, maybe the noisy samples are defined as some like we flip the labels of the point, or the labels are polluted by some people, and it's about some label noise. But what you mentioned is about like feature noise or some kind of other noises, and I think they can be modeled in our framework, because actually if the features are polluted, also the labels need to be changed. It can be viewed as another kind of label noise. And also to differentiate hard samples and noisy samples, there are many other works to do so. For example, you can look into the dynamic during our model training, and we can see how the prediction error and also the uncertainty of each sample changes along the model training. And many methods use such kind of dynamic information to identify hard samples and noisy samples, and they may use them in the training of large models, and it turns out as it performs very well. Yeah. Yeah, please.
Expectation of how you measure the heterogeneous, how you measure the heterogeneous intensity of the data.
Actually, here the data heterogeneity is quite a vague definition, and it contains so many parts. For example, like here, it may refers to subpopulation structures, hard samples, noisy samples, and even different generating process. Actually, in the literature, there is no explicit definition of this term, but during our third part, we just provide several tools to understand different or some specific kind of heterogeneity. For example, in our first tool, and in our first tool, we just provide the predictive heterogeneity, which captures the heterogeneity that affect model prediction. And in this way, and for this kind of definition, it cares about the mutual information that X could provide for prediction Y. And what I have to say is only about one specific forms of data heterogeneity. And also for other, and also data heterogeneity is about maybe hard samples, noisy samples, and also about data geometry or something else. And we only have clear definitions for some specific forms. Any more questions?
May I have a question?
Yeah.
I'm wondering, do you consider any data heterogeneity in different data modality, for example, 3D and 2D images? We'll find some.
Yeah. For this tutorial, for the experimental results, we only share about some on the tablet data set. However, some of our methods were using other modalities like graph data and image data. By the way, do not put it here. Yeah.
Sorry, one more question is fine. By the way, you mentioned the clip you used in the section 2. There are two encoder, decoder, text encoder, and image decoder. Do you think maybe in a high level of representation of the image, will there be some shift regarding this kind of shift between text, knowledge, and the image?
You mean the shift between knowledge?
Yeah, the different modalities.
Yeah. I think it will be because I think like the alignment for multimodality language models or big models is also an important research direction. And many other researchers try to explore how to better align different modalities in some like multi-model language models. Yeah, thank you. Yeah. Also, if you have maybe more questions after our tutorial, and you can just email me, and maybe we have Slack, and I'm also in Slack. Yeah. I think that's all. Thanks for listening, and also thanks for your time.